Hello there. Let's take a look at feed-forward neural networks. Now, what we have in front of us is a multi-layer neural network. Now, this can be called as a feed-forward neural network if it satisfies certain conditions. Now, in this network, the information only passes from the left to the right. That is, in the forward pass, the information comes inside via the input layer, goes through the hidden layers, and then finally goes to the output layer. The information does not loop between the two hidden layers, neither it loops within a single hidden layer or within a neuron itself. These are some primary conditions. Let's take a look at an example. Now what we have here is an image classifier in the form of a feed forward neural networks. What we have done is we have abstracted all the hidden layers and the neurons into one big neuron here. Now the input is an image of 4 by 4 pixels, so that is 16 pixels. So hence you have 16 input nodes. You have an abstracted hidden layer, and on the output side you have 10 nodes because the input could be numbers from 1 through 10. In the output stage, it gives you the probability of it being a 1 or a 7 or what it thinks the input is. For example, if the input is 1, a well-trained network should give you this kind of scores. This is just an example, of course. So it should think that the 1 is 99%. So it's pretty confident that the input 1 is a 1. It also thinks that 7 is 75% because 7 is very close to 1. So this is how an image classification works with a feed-forward neural network. Now let's take a closer look at a single layer and let's try to understand the different components from a low-level perspective. Now here what we have is one single input node, we have one neuron, and we have one output node. So input takes a pixel, it does pre-processing to the information, and then it passes to the hidden layer. Now the hidden layer has weights multiplied by the input pixel, of course. It adds a bias to it, and it also passes through an activation function. It decides whether to fire or not to fire depending on this specific output, which is weights into input plus bias. Then it passes this decision to the output layer. The output layer also has an activation function. This activation function tells you the probability of the output. For the hidden layer, you could use one of the many activation functions. These days, the popular one is the rectified linear unit. This brings in non-linearity, reduces the calculation, reduces the density, and thereby the overall complexity of the function. The hidden layer functions are used to make micro decisions. So this function's output is 0 if the input is less than 0 or any negative number, and it is what the input is if the input is greater than 0 or any positive number. Which activation function to use will really depend on the use case or the problem you're trying to solve. The output layer activation functions are many as well, and some popular ones which can be applied are sigmoid and softmax. Now sigmoid is used for binary classification. So when you have two classes and you need the network to decide between the two classes, then sigmoid in the output layer does a wonderful job. So it basically converts all inputs between 0 and 1. So it's very easy to differentiate between the two inputs. Softmax is used for multi-class classification. So where you have multiple classes, it converts the input into an average probability of all inputs. So basically it gives you the probability of one input over all the inputs. This is like the one we saw in the example with the image classification in the last video. So now we have a little bit more idea about the structure and the internal components of a feed-forward neural network.